Good afternoon, and welcome to session H3, Advancing Hydrology Methods for Flood Risk Assessment. I'm Karen McHugh, CFM, and I'm the Missouri State NFIP Coordinator, the ASFPM Region 7 Director, and your moderator for this session. I hope that everyone has had a great conference so far. Please remember that questions are live, so do not wait until the end of the session to get your questions in. I would like to take a moment to recognize and thank HDR for the sponsor of the session.
We own everything we do, our word, our actions, and our company. That accountability empowers us. It motivates us. It drives us to do things right for the people we work with and the communities we help build. It inspires us to connect. No matter where the opportunity lies, we bring together people and ideas from across the globe.
Creative and analytical, pioneering and practical. And over the past century, we've learned it takes more than knowledge and talent.
It's what's unique in each of us, our experiences and our perspectives, that have the power to make each other the best that we can be.
We add beauty and structure. We help protect our natural and built environment with sustainable design and resilient infrastructure that guards against flooding and enhances our water resources. Together, we face tough decisions, proactively, thoughtfully, and cost-effectively.
Transforming the world, one community,
one project,
one design at a time.
Thank you, HDR, for all that you do to help mitigate flood risks. Now I'd like to introduce our first speaker, Clark Barlow, PE, CFM, who will present Adapting 1D Hydrologic Methods for 2D Hydraulic Applications in Clark County, Nevada, and Orange County, California. Mr. Barlow is a senior water resource engineer with Atkins and an expert in complex H&H modeling. He has played a key role in several challenging modeling projects across the United States. I'll turn it over to Mr. Barlow for his presentation.
Hello, my name is Clark Barlow. I'm a senior engineer with Atkins, and I'm excited to be here presenting at the virtual ASFPM conference. I'm here to talk about adapting 1D hydrologic methods for 2D model applications. And I'll be discussing this topic in the context of two case studies, one in Clark County, Nevada, and the other in Orange County, California. So starting with the Clark County, Nevada case study. Clark County, Nevada, if you're not familiar with Clark County, is in southern Nevada. It's where Las Vegas is located. And the study area for this case study is on the west side of the valley. It's actually within the city of Las Vegas. It's an area that's growing quite a bit. And the area is, if you've ever been to this part of the area, it's in Summerlin. And this particular development is referred to as Summerlin West. It's an 8 square mile development denoted here by the green boundary. And the entire watershed area that encompasses and impacts this development boundary is 21 square miles. The watershed is characterized by steep terrain. It's a very alluvial, and it's very picturesque. And so there's a lot of interest and desire to develop this area. However, there's no flood control and no flood protection at the moment. And so that was the impetus for this study, was to better understand the complex flow patterns in this area. Specifically, we wanted to establish the 100-year existing condition flow rates and velocities so that as proposed flood control designs were developed, that they could be compared against, the existing condition flow rates and velocities to make sure there were no adverse impacts in comparison to what was there previously. Our approach to analyze this problem was to use HEC-RAS 2D as the modeling engine. We used variable cell sizes ranging from 20-foot cell sizes where we needed a lot of detail and up to 100-foot cell sizes where not as much detail was needed. We used a rain on grid approach. And what that allowed us to do is it allowed the model then to figure out where the drainage paths should go. As you can see, if you look at the blue flow patterns, you can see that flow sometimes splits and then comes back together. And so we felt like it would be better to let the model figure that out instead of us trying to delineate manually where the basin boundaries should be. We also elected to model the entire watershed and instead of trying to confine the model to the development boundary. And the reason for this is if you look at that green development boundary, you see that flow sometimes comes into the boundary and then back out. And then also you see many locations where flow enters the boundary. And so if we were to confine the model to that development boundary, it would be a very challenging exercise to try to figure out what that inflow boundary condition should look like. And so ultimately, that's what led us to model the entire watershed. As we started this process, we encountered several challenges, particularly as we tried to follow the drainage design manual within Clark County in the context of these more advanced two-dimensional models. And there were three areas that we ran into challenges and came up with what we felt like were good solutions. The first is in regards to the rainfall depths. As you can see, the blue lines are isohyoidal lines, which are areas of uniform rainfall depths. And so on the west side of the watershed, you see a rainfall depth of 3.4 inches, and on the east side, you see depths of 3.4 inches, and on the west side, you see depths of approximately 4 inches. Not a huge range, obviously, but when you get about 4 inches of rain over the entire year, that 0.6 inches can make a big difference. And so we wanted to have some way to be able to capture that variation in rainfall. Infiltration was another consideration, particularly as we were looking at doing the rain on grid approach. HEC-RAS doesn't, at least the version we were using, didn't have the ability to model infiltration. And so we had to come up with a way to quantify that. And then depth area reduction factors, which is a way to adjust rainfall depths based on the upstream area, was something we had to consider, something that's done commonly within Clark County, but is a hard concept to apply when trying to fit that within a 2D model framework. So first, looking at the rainfall depths, the solution we came up with there is that the limitation we ran into is that HEC-RAS only lets you specify one rainfall depth for each 2D area, and so the only way that we could introduce a varied rainfall depth was to break up the domain into multiple 2D areas. And so you can see we broke it up into 4 different sub areas. And then within each of those 4 2D domains, we were able to specify a different rainfall value. And so it gave us a little bit more control over how much rainfall to put in different parts of the watershed. So for instance, in the area that was 1.7 square miles, the rainfall depth was closer to the 3.4 inches. Whereas in the area that was 5.9 square miles over on the west side, the rainfall depth was closer to the 3.7 and 4 inch range. And so then we were able to connect those 2D areas using 2D connection lines, which basically act as weirs that follow just the ground profile. And then that would control the exchange of flow between the 2D areas. And so we were quite pleased with that approach, and it seemed to work very well. As far as infiltration, again, as I mentioned, HEC-RAS doesn't have the ability, or at least in the version we were using, didn't have the ability to model infiltration. And however, that's an important part of the hydrologic analysis. And so what we elected to do was use HEC-HMS to compute the rainfall losses. And then we took the rainfall excess amounts from HEC-HMS and used those values as the direct rainfall input into the HEC-RAS model. And so that we were happy with that approach. It gave us a level of comfort that we were accounting for losses, and then applying the rainfall excess as an adjusted sort of rainfall depth that had already accounted for the infiltration. The depth area reduction factors was another challenge, and essentially depth area reduction factors allow you to look at the total upstream area and then use an adjustment factor to reduce the rainfall, to account for the fact that the storm isn't going to fall uniformly over the entire large watershed. And then as that watershed gets smaller and smaller, as you look at smaller watersheds, then that the impact of that adjustment becomes less and less. That was a difficult concept to think about and apply in a 2D model. And what we came up with and finally realized is that the best way to do this was to not apply a rainfall adjustment at all, but to apply the rainfall values without any adjustment, and then wait until flow rates were computed to then look at making an adjustment. And the reason for that is because at any given point within the model, you're going to have a different upstream area. And so, take the point there at the top right where it shows 807 CFS. What we would do then is inspect the upstream area at that point, figure out what the corresponding DARF value is, and then apply that DARF adjustment on the flow rate. And so we were pleased with that approach. And in fact, as we compared the results of this modeling effort with a 1D model that covered at least a portion of this watershed, we found that the results were actually quite comparable within the 10, 15, 20% range. Now, a lot of that variation is because of the fact that 2D models are inherently different than 1D lump parameters models, and so you would expect that kind of difference anyway. And so the fact that we were able to make some simplifying assumptions and still be within a reasonable range, gave us some good confidence in the approach we used. Now moving on to the Orange County case study. The Orange County study is within the Seal Beach watershed. It encompasses several different municipalities: the city of Huntington Beach, city of Seal Beach, unincorporated Orange County, as well as several others. It encompasses three major sub-watersheds: the Bolsa Chica watershed to the north, which is depicted here in green, the East Garden Grove Wintersburg watershed, which is the one depicted in blue, and then a smaller watershed called the Sunset watershed, which is wedged in between the two, and it's shown here in purple. The total watershed area is 66 square miles, and it includes 23 miles of studied streams. It's a very urban area, highly urbanized, very different from the watershed that we just looked at in Clark County. And so came with a lot of its own challenges. In fact, probably deserves its own presentation and probably will at some point. The objective of the study was to carry out an updated hydrologic analysis using the best available data, and then to develop a 1D, 2D hydraulic analysis that used the hydrograph output from the hydrologic analysis as input into the hydraulic analysis. And then the floodplains that were generated from the hydraulic analysis would then be used to produce updated flood maps for insurance purposes. And that's still an ongoing effort. The hydraulic model was built using HEC-RAS. It was a combined 1D, 2D unsteady model. The 1D domain was connected to the 2D domain by using lateral weirs, and the 2D domain was comprised of 50-foot cells, which still resulted in a fairly large and sizable model. The inflow hydrographs were applied in the 1D domain using the inflow hydrographs from the hydrologic analysis, which for this study followed the Orange County unit hydrograph method that's prescribed in the Orange County Hydrology Manual from 1986. And so the fact that we were using the hydrologic methods from 1986 to try to apply that to, this complex 1D, 2D, unsteady model became quite challenging. And there were two areas I want to point out where we ran into some specific challenges. The first was, again, in the application of the depth area reduction factors, and the second was in the application of the lag time and time of concentration calculations, which are fairly unique within Orange County. So first, the DARFs. DARF values are typically applied like we talked about for a single catchment area based on that drainage area. So you look at the drainage area and figure out which DARF value corresponds to that. Now the Orange County Manual states that that catchment area is the total drainage area contributing runoff to the point of concentration where the design discharge is to be calculated. Now that became quite challenging to apply in our case because there wasn't just one design discharge that we were interested in, but we were interested in multiple discharges along the course of the as you move downstream in the channel. And so if you used one depth area reduction factor for one concentration point, when you move down to the next concentration point, you may have enough area now at that point where you should be in a different DARF. However, you've got, you had a concentration point upstream that you needed a different DARF for. And so in order to apply, that criteria strictly, we really would have needed separate models for each DARF that corresponded to the upstream area of each concentration point. In other words, if you have 20 different DARFs that correspond to different areas, you essentially need 20 different models for all those DARFs, and then you go and look, and pull the model, for that particular DARF that corresponds to the concentration points you're looking at. Now, for the number of concentration points we had, the number of DARFs that were there, and the number of return periods we were modeling, we were looking at potentially, hundreds of models, each with different rainfall depths that were adjusted for a different DARF. And that the prospect of doing that was just crazy, to be frank. And so we brought that up with Orange County and came up with a simplified method that was more practical for the purpose of our study. And so that simplification is outlined here. Essentially, the upstream area for each concentration point was evaluated, and a corresponding DARF value was then applied to the rainfall values, not for that entire watershed, but for additional sub areas that came in between that concentration point and the next upstream concentration point. Now, although that resulted in an over prediction of flow rates at the concentration point, the hydrographs from individual subbasins coming in were more accurate. And really, it was the hydrographs from those individual subbasins that we cared about the most, because it was those hydrographs that were going to be used as inputs into the hydraulic model. We weren't interested in using the hydrographs at the combination points because the 2D model, already has flow coming into it from upstream areas. Now, like I said, the flow rates computed at concentration points, because they weren't used as inputs into the hydraulic model, it wasn't as important that, that those concentration point flow rates may be a little bit overestimated. Now, as far as the lag time and time of concentration goes, the Orange County Hydrology Manual, again, from 1986, actually requires a separate rational method analysis be completed to develop time of concentrations for unit hydrograph studies. In other words, if you have a single watershed that you're running within, HEC-1, you need a separate parallel model of that same watershed using the rational method to come up with the time of concentration that you can then transfer into that unit hydrograph or that HEC-1 model. Now, for one watershed, that's not such a big deal. But when you're looking at 50, 60, 70 sub-watersheds, and now 50, 60, 70 separate rational method models, then it becomes a big deal. Specific instructions for how to do this weren't really written into the manual just because that application wasn't very common back when the manual was written. Now, if you think about, so we sort of had to think about this, and come up with an approach that we felt like would be appropriate. Now, if you think about the rational method analysis, at least in the Orange County manual, it requires a couple of things. It requires the delineation of an initial sub area, which is really small because that initial, time of concentration, is so slow. That time is very critical to the overall time of concentration in the watershed. And then each subsequent sub area size is supposed to be no greater than 4 times the area of that smallest sub area. So now you're not only looking at a parallel rational method model, but potentially one that's subdivided over and over and over again, to comply with that criteria. And so these were the kinds of conversations that we had, with Orange County, to try to figure out, okay, what is the most practical way, to apply the manual in a way that satisfies the objectives of this study. And we came up with an adaptation. It was important to the county and something we recognized and understood, that the rational method approach still be followed, something that was prescribed and something that was important to them. And so, but one area where there was some compromise is that the sub area or the sub basing area guidance was shown to be not very sensitive. We ran a sensitivity analysis and showed that, if we increase the sub basin size, more than the 4 times, sort of threshold, that it didn't really impact the flow rates dramatically. And so that was an area that was relaxed a little bit. Another adaptation is, that some areas, there was this area that's shown in that's marked by number 1 was a tributary that wasn't part of our detailed study streams, but it was a tributary that came into the project area. And we had initially subdivided that the same way we had subdivided along the study streams. However, because that was going to result in so many more rational method models, we elected to just combine those sub areas into one large sub area, which is not something we would have done normally, but was an adaptation that that gave the county some level of comfort, and in the end, resulted in a reasonable flow rate. In fact, if you look at the results from the study in comparison to a previous study done, as well as the FEMA effective flow rates, even with when comparing the concentration points, which we felt like were over predicted, we were still very close to those previous studies. A couple of lessons we learned through this process are that many hydrologic criteria manuals, particularly ones that haven't been updated in some time, just are not well suited for unsteady hydraulic model applications. let alone 2D modeling. Just the unsteady, concept is something that requires some adaptations, of that criteria to be able to use it for. It also, another lesson we learned is that there really is a need, I think, to standardize some of these inputs, rainfall, DARFs, how to handle infiltration, time of concentrations, and lag time, for these 2D unsteady applications. And that's only going to become more important, as 2D models become more widely used and accepted. And then a third lesson we learned is that it's just key and extremely critical to have an upfront discussion with the project team, both the consultant and the client, regarding the modeling approach, and what simplifying assumptions are going to be used, just so that everybody's on the same page and you have buy-in from the very beginning, and that requires, both an understanding of the 2D models and how they work, as well as an understanding of the criteria that's being applied. And so that discussion, may require, getting into the weeds a little bit and, talking about, unit hydrograph methods and routing and infiltration and DARFs and, and how that might impact, particularly in a very large study such as this, where a change or an interpretation of the manual one way or another, can really impact, both the budget and the schedule and the overall success of the project. That's it. I appreciate the opportunity to present this topic. Hydrology and hydraulics is something that's near and dear to me. And so I'm grateful for this opportunity to have, share these insights. And with that, I'll take any questions. Thank you.
Thank you, Clark, for your time today and for your informative presentation regarding the capabilities and advancements of H&H modeling tools. We received several questions for you in the question and answer section, and I'd like to open that up for discussion. Your first question is from Charles. He asks, what temporal rainfall distribution was used?
Yeah, thank you for that, Karen. So in Clark County, the Clark County manual has a temporal distribution curve called the SDN3 curve. And it's a temporal distribution that was developed by the Army Corps of Engineers back in 1988. And so that's where that temporal distribution comes from. As the watershed gets larger in size, there's other curves that are recommended, but SDN3, I believe, is the one that fell within the watershed size we were looking at.
Okay, this question comes from Hayden. Were there multiple sites represented with 2D connections that were flow interchanged between 2D flow areas, or did you design the parameters so that there was only one location where the flow interchanged to adjust 2D flow areas?
That's a really good question. And, I could have spent a lot more time on that concept because it was a fairly sensitive part of the model. That 2D connection line isn't as straightforward as we assumed when we started that process. What we ended up doing is we tried to design the perimeters of those 2D areas to fall mostly along watershed or sub-watershed boundaries. And so we did confine those 2D connection lines to the areas kind of in the lower part of those boundaries where we saw more flow going between the two 2D areas. And that seemed to make the model a little stabler. There wasn't as much issue with trying to get the model to run that way. And so so we did try to be intelligent with the placement of those perimeter boundaries, as well as the placement of and the length of those 2D connection lines.
Okay, I think we have time for another question from Greg. Did you consider using HEC-HMS with 2D diffusion wave transformation? It runs the HEC-RAS engine under the hood and can handle infiltration and base flow.
That's a really good question, and another reason why I really enjoy this conference, because I always learn new things. And so we did not try that because I wasn't aware that that was a possibility. And so thanks for pointing that out, Greg, and that's something that we will, definitely look into in the future.
Okay, I think we have time for one more, and this question is from Kurt. I was surprised to hear that you can't have variation in the rainfall or the infiltration parameters in each individual grid cell instead of a single rainfall value in each subdomain. Is that still a limitation in the model, or has that functionality been added?
Yeah, so that's a good question. So we were using HEC-RAS version 5.0.7. In that version of the model, there is a limitation where you could only specify one rainfall depth per 2D area. I understand that you can. That's now been changed, so I don't believe you have that limitation anymore in the new version of HEC-RAS, and I believe that's something Mark will talk about more in his presentation.
Okay. All right. I think that's all the time we had for questions. Now I'd like to introduce our second speaker, Mark Forrest, PE, CFM, who will present transformations in hydrologic methods without transforms, testing of new HEC-RAS 6.0 rain on grid solutions. Mr. Forrest is HDR's Senior Business Class Leader for Floodplain Management and Surface Water Modeling. He is responsible for managing HDR's technical practices in these disciplines. Mr. Forrest has over 38 years of experience in floodplain management, H&H modeling and drainage, and floodplain design in both the public and private sectors. I'll turn it over to Mark for his presentation.
Good afternoon. I'm Mark Forrest. I'm the practice leader for floodplain management and surface water modeling for HDR. Thank you for joining us this afternoon for this session. I look forward to next year when we can actually do this in person in Florida rather than in this virtual environment. But we'll make do with the virtual environment. And today I'm going to talk about testing the beta version of HEC-RAS 6.0 for the gridded rainfall and infiltration functions on 2 watersheds in the Houston area in response to Hurricane Harvey. And first of all, it's important to kind of put in context to how these new features differ from what's in RAS currently. You can do rainfall runoff modeling in RAS 5.07, but you're limited to the assumption of a homogeneous rainfall excess over your entire domain, requiring that you break up your model into multiple interconnected domains in order to treat any kind of non-homogeneity. So it's a bit awkward to do the level of sophistication you can do in the new version. What the rainfall runoff simulation in RAS does is replace the unit hydrograph transformation, which assumes a much more lumped kind of parameter approach to determining how the runoff accumulates within your watershed to the point of interest. The simulation can be done with either the diffusion or the full momentum solution. 507 validates quite well against HMS. This has been tested by HEC. We tested it on a number of watersheds. One example is this one from Rincon, New Mexico, where this watershed was simulated using HMS originally. The rainfall excess from HMS was applied to a 2-dimensional grid within RAS to see how well it would replicate what HMS produced. And so the volume is going to be identical, as you can see in the comparison hydrographs, because it's using the same rainfall excess. So by definition, it's the same volume of runoff. The difference being the replacement of the transform with a very dynamic simulation of the rainfall from all portions of the watershed accumulating in the main channel to the point of interest. The peak was very similar, but the time of peak was only slightly offset, so they compared very well to one another. And it's able to do that because RAS sees that subgrid level of detail, which most 2D models simplify the terrain as either as a single elevation for each grid element, represented as a triangle or a rectangle or a square, as opposed to being able to see the subgrid terrain detail that RAS does. So RAS if you imagine that this is a grid cell within your model, it cuts a cross section at each cell face. You can see that when flow enters at this cell face, it only has an opportunity to leave this cell face at very low flows. It has to get deep enough to interface with the two sides before there's going to be interaction between this cell and the adjoining cells on either side. So that allows it to see a preferential flow path through your domain. That's real important to doing rainfall runoff modeling and be able to capture those unique hydrodynamics of how flow is propagating through the watershed. So version 3 of, or beta 3 of version 6 of RAS adds a couple of new features that are really key to this process. One is gridded rainfall. So by being able to identify the time series rainfall that's occurring at every point in your watershed, every grid cell within your watershed, allows you to simulate the behavior of a storm that's moving across your watershed or down your watershed, which would obviously change where that rainfall excess is occurring and then how it ultimately propagates through your watershed. The other is spatially variable infiltration. So with that rainfall that's occurring here, it's falling on different types of surfaces that have different runoff characteristics. Being able to capture that at the locally specific level combines that locally specific rainfall to a very locally specific runoff computation, and then allowing that two-dimensional solution to then accumulate that rainfall, that runoff within your watershed to your point of interest. So our two test data sets that we applied to this test, it's a limited test of some of the features. One is a gauged watershed, which is Peach Creek at Spangora, and which is this one. And the other is an urban catchment that's fully urbanized and ungauged. Hurricane Harvey produced very substantial amounts of rainfall over the Houston area. In our larger watershed in Peach Creek, 22 inches approximately during the course of that event, as compared to almost 28 inches in our urban catchment. When you apply that gridded rainfall to RAS, it gives you the ability then to simulate what RAS is seeing in that gridded data set, which is what you're seeing here. This is the RAS mapper animation of the Hurricane Harvey event that is documented in the new events condition window layer and within your RAS mapper window. And you can simulate both the precipitation incrementally as well as cumulatively during the course of that event. This is the incremental precipitation. So what it's doing is replacing the traditional transform, which is a unit hydrograph. And unit hydrographs are based upon the assumption of a pretty standard shaped watershed, and usually a dendritic watershed, that does not have substantially unique conditions. Like this watershed here is very long and narrow, and so it wouldn't fit the standard shape of a hydrograph that most unit hydrographs are based upon. Some of them include a shape factor that allows you to compensate somewhat for those unique differences, but it certainly doesn't replace the ability to simulate the more dynamic response of that runoff within each individual watershed in its own unique characteristics. A lot of times also people assume that the same time of concentration will apply to all the events that they're going to simulate within that watershed, a 10-year event, a 100-year event having the same time of concentration. But that's not true, because a very frequent event is going to produce lower depths and velocities within these channels, and therefore a longer travel time or time of concentration than an extreme event that produces greater depths, greater velocities, and shorter times of concentration. So by simulating it dynamically, you'll automatically account for those differences from rainfall event to rainfall event, as opposed to having to try to modify your time of concentration to account for those differences. Runoff accumulation is going to be much better defined, obviously, than with an overland flow model, since it's able to capture a lot of those very unique watershed conditions that exist. The surface for overland flow is going to vary depending on the characteristics of that surface, where the defined channels are and what their conditions are, what their roughness are, is the storage that's taking place within the watershed, and if they're behind either impoundments or behind roadway embankments, will affect how flow propagates through the system. And then if you've got conveyance systems within your watershed, that may also influence how water accumulates and propagates. The roughness of those surfaces is obviously key, that in the spatial variability of that roughness, as well as the rainfall and runoff, and all influence the velocity that leads to the time of travel to get to your point of interest. Rain on grid considerations include having properly characterizing the surfaces you're dealing with, as well as the complex factors that affect the rainfall losses that get you to an excess. For example, interception is by the plant canopy is uniquely different when you've got a situation where you have sagebrush or turf or very, very dense trees. They're all going to have their own unique interception characteristics, depression storage, surface wetting and infiltration that's spatially variable with soil type and soil profile. Not all hydrologic methods really can account for all these factors in the same way, if at all. And oftentimes the parameters are lumped, which require you exercise some judgment about how you pick the range of possible parameters without the ability to separate out these various factors by themselves. Terrain accuracy is obviously very key. Proper meshing and characterization of your surface is going to be key. So the potential sources of error when you're doing this type of simulation, the rainfall is going to be one of your biggest potential sources of error, and usually is in a hydrologic model. When you don't fit the observed data, you should look at the rainfall first, because it's usually your culprit, your largest culprit. Make sure that rainfall also has been adjusted to your local time, because NOAA publishes their data for Greenwich Mean Time. So when you're comparing to observed data, that adjustment has to have been made first, or you're going to mismatch depending on where you are. The terrain data and bathymetry really defines that stage velocity relationship that influences flow accumulation. So if your surface is not properly represented in the terrain data, you're not going to accumulate the same way. This is an example of the same location, this one being a LIDAR data set, this one being a 1/3 arcsecond data set, and a cross-section cut through the same location within those two data sets looks like this. Clearly, this is not going to behave the same way as this one does. So characterization of the surface, and we talked about those, as well as the solution scheme you use may have a difference in the outcomes. The rainfall is really key to the behavior, and in this case, we're using an hourly data set, which is really not, it's too coarse. There are, during an event like Harvey, there were very intense bursts of rainfall that occurred at the sub-hour level. And by averaging the values at the hourly level, you're not capturing those shorter duration, intense bursts within that rainfall event that could be critical to the peak discharges, especially in a smaller watershed. So adjusting that gauge adjusted radar data set, rainfall data set, using adjustment techniques and ground truthing techniques to get better discretization would improve the results. But here's what we got when we tested terrain effects. The one on the left is a very detailed LIDAR terrain data set. That's an excellent terrain data set. The one on the right is that 1/3 arcsecond terrain data set that's very coarse. There's no other model differences between these two simulations other than the terrain. So swapped out the terrain and reran it. And what you see there is obviously a very different outcome in terms of flooding extents between these two simulations, which also produces a different outcome in terms of peak discharge at points within the model, where the upper line is the coarser terrain data set and the blue line is the more refined data set. So takeaway there is terrain data set makes a huge difference in your outcomes when you're looking at those kinds of differences in inundation and peak. So the loss methods that are available in this current version of the RAS beta are these three. And it's important to note that these are obviously very different in how they get parameterized. Deficit and constant requires a much coarser lumped parameter data set. The SCS curve number method can be more specific to cover type, cover density, and soil type. So it's a little easier to physically characterize your parameters based on your watershed characteristics and your vegetative characteristics. This is a modified version of the curve number method. So what HEC did was modify the curve number method to allow for initial abstraction makeup, and the user can define the period of no rainfall that would allow the initial abstraction to return and be applied again, and also allows the use of a constant infiltration rate at the tail end of your simulation, where the infiltration rate becomes constant or asymptotic. You can apply that constant infiltration rate at the tail end, and that's a flaw in the current curve number method, because the losses become zero after a certain point, which the traditional curve number method is only applicable to the 24-hour duration that it was developed for and can't be applied beyond 24 hours. These modifications allow you to be able to do that, use the curve number method for longer than 24-hour periods, which is worthy of additional testing. But as you'll see, our results are not bad at all for an event that's actually 5 to 6 days long. Green and amped describes the infiltration curve a little more explicitly. I didn't test it in this particular instance, but that would also apply to longer duration events. So our Peach Creek example uses the NLCD data set for land use, the 1/3 arcsecond for the terrain, so obvious opportunity for improvement, the Sergo database for the soils, and I tested both those two loss methods. And here are the results. The red is the observed data. This one here is the curve number result, and this one here is the deficit and constant loss result, which obviously both of those need a little bit of improvement. They're not bad for a first cut and for a very rough cut, applying it to these models. So without any kind of modification, just reasonable estimates inputs were coming close, which means that we could get a better fit with adjustments. What would those adjustments be? They'd be a refined GAR that gives us that sub-hour detail and probably improved results for depths, better terrain data, better land use classifications. The curve number method needs to consider minor soils, not just the dominant soils. Verification of vegetation type and cover density from a better land use data set other than the NLCD. The curve number needs to be refined based on soils and cover. And in some cases, you also need to make sure your target is good. Assuming that USGS published hydrograph is accurate can be incorrect in many cases. We know in this case, this hydrograph has been validated, but it's something you should always assume that there's potential source of error there as well. So in conclusion, what we found is that the revised curve number method really has great promise for overcoming traditional limitations to this method to the 24-hour duration. that initial abstraction makeup and the steady state infiltration rate really are nice adjustments to that methodology that give me a lot more confidence that you can apply it to longer duration events. Spatially specific losses and in rainfall vastly it reduces lumping of parameters, particularly a moving storm across your watershed or that spatial variability that's lumped into the whole watershed is a really gross oversimplification when there's non-homogeneity. This allows you to actually capture that non-homogeneity at a very spatially specific scale. The tools are very versatile for doing sensitivity testing and refinements. You can modify the tabular values really easily to capture your error bands. The overland routing is vastly superior to the unit hydrographs, and that subgrid terrain detail really lends itself well to doing overland routing accurately. The quality of the inputs is key to the outcomes. So making sure that all of those inputs are good will improve your results for sure. And it's also interesting to note that this solver is got such good promise in the eyes of HEC that they've added it to HMS 4.8 as well. It's the diffusion wave solution, but it is the RAS 2D to diffusion wave solution that's in RAS, has now been incorporated into HMS as an option to transforms. So obviously they see promise in this particular approach, and it's beginning to make both models look a little more the same. And the advantage of this is that now you can use a lot of the other features in HMS for rainfall runoff loss modeling that aren't in RAS. So with that, I will open it up for questions.
Thank you, Mark, for your time today and for your enlightening presentation on using rain on grid solutions. We have several questions for you. The first one is from Hayden, who asks, are there any good tools or resources to use you used to develop the gridded precipitation input and associated timing?
Can you hear me now? Yeah. Okay. So that question seems to be related to my particular test, which was an observed event, Hurricane Harvey. There are some other questions I see regarding hypothetical events as well. In our case, we used two sources of information for testing. One was the NOAA data, which is a gridded data set that already has the information at a 1 kilometer interval and at a 1 hour time increment. There are other tools out there for adapting data sets like HEC METView, which will allow you to also incorporate hypothetical events.
Okay, and Jeff asks, related to Hayden's question, my understanding is that the gridded precept file format is well suited for simulating historical storms, but not for standard precipitative design storms or FEMA reoccurrence intervals. What is your experience with creating gridded data for precipitative events? Oh, predictive events, sorry.
Yeah, that's a really key question, because that's something that we're obviously going to have to put some investment in now that we have the ability to simulate these kinds of events. We need to have the tools able to parameterize a hypothetical event. Like I said, HEC METView has the ability to generate the rainfall associated with a probable maximum precip event using different types of patterns. The data can be imported directly from a spreadsheet as well, from Excel directly into DSS, and then read from DSS into RAS. So there's probably a number of different tools you could potentially use to create that gridded data set. But HEC METView is probably the one that's going to show the most promise for getting that data in the right format for the HEC products.
Okay. Mark T asks, based on your assessment, Do you see that this beta version can do most of hydrologic assessment that a HEC-HMS model does? Has there been any comparison?
No, this is the question about proper tool for the proper job. You don't use a screwdriver to pound in a nail, and you don't use a hammer to screw in a screw. There are things that HMS are capable of doing, like much more complex simulations. Base flow is what mentioned in one of the questions to the previous speaker. There are things you can do in HMS you cannot do in RAS. Likewise, there's some things you can do in RAS that you can't do in HMS. For example, the two-dimensional solution in HMS is limited to the diffusion wave solution. So if you're trying to model complex behaviors where you have significant contractions and expansions or complex hydraulics, HMS is not going to be able to capture that, but RAS will. So it's leveraging the right tool for the right job, and depending on what you need to pull out of the output.
Okay. Chris asks, with lumped rainfall runoff models, the parameters like time of concentration, routing parameters, etc., are essentially hydrograph shaped parameters that give users options when calibration data is available. Is there anything beyond N values that can be used to shape 2D hydrographs?
No, but that's the process you have to go through to try to make a transform model in HMS fit your observed data. What you'll find, I think, when you run a rain on grid simulation is the objective is to get the flow conditions represented correctly in your model, and then you should be fitting the data much better. So you should have to do a lot less of that type of data manipulation in order to make your model fit when you're actually modeling the physical characteristics of your watershed with more accuracy. So it's focusing on where your inaccuracies are.
Okay. I am not an engineer, so I'm sorry, I'm mispronouncing some of these terms. But what recommendations would you have for applying rain on grid near more developed streams if bathymetric data is not available?
Without the bathymetric data, you're not going to pick up the channel behaviors as accurately. So you can certainly modify by approximate methods the channel conditions. And RAS also 6.0 also includes some vector modification tools for the terrain that will make changes to the terrain on the fly for incorporating things like bathymetry. So you would have to approximate it if you don't have good data.
Okay. Have you tested bridge routine in 6.0 and noticed any stability challenges?
Yeah, the bridge routine in 6.0 is the same, essentially the same set of lookup tables that are created in a 1D unsteady solution. It uses it to determine the loss across the bridge from everything but friction, and that's done at the 2D level. So you'll have the same challenges oftentimes with stability that you do with a 1D unsteady bridge.
You're getting some great questions, Mark. Diane asks, were you able to do any verification from USGS high water mark assessment with Harvey?
Yes, actually we have. It's not part of this presentation, but we've spent a lot of time on that.
Okay. Let's see. Great content. Can you comment on the applicability of diffusion wave versus full momentum with rain on grid modeling?
Yeah, I didn't actually present that, but it was one of the things that we did test was the difference between those two solution schemes. There was a minor difference in the results when I went to full momentum compared to the diffusion wave solution. You would see more of a difference when you have flow storage happening behind roadways and bridges.
Okay. Sorry. Mark, I think we have time for one more. Have you considered how to adjust the area depth reductions where simulating design storms? a significant challenge for 2D modeling design storms in large areas.
It very much is. So that spatial variability of precipitation is a key factor. The larger your watershed, the more critical that is. So I think that's going to be a focus of attention again on the use of tools like HEC MedView to develop hypothetical events. That's where it takes a fair amount of experience, how to do a centering approach to your storm event, either using an observed pattern that's adjusted or developing a hypothetical pattern like the ones that are generated in the HMR documents.
Okay, thank you, Mark. And now I would like to introduce Ed Dickson, PE, CFM, and co-presenter Alicia Lanier, PE, who will present utilizing a citywide rain-on-mesh analysis to identify flood risks for the city of Fayetteville. Mr. Dickson is an associate in Freese and Nichols in the Charlotte, North Carolina office who specializes in watershed-based H&H analysis, flood mapping, and flood management projects across the United States. Ms. Lanier supports the city of Fayetteville, North Carolina in managing their citywide watershed master plan program. I will turn it over to Ed and Alicia for their presentations.
Good afternoon. I'm Ed Dickson with Freese and Nichols, and I'm here to present with Alicia Lanier with the City of Fayetteville on utilizing a citywide rain-on-mesh analysis to identify flood risk. I'll turn it over to Alicia to get us started.
Thank you, Ed. I'm really pleased to be working on this program with y'all and participating in this talk today. My name is Alicia Lanier, and I am a Stormwater Project Manager in the Public Services Department at the City of Fayetteville. To date, my role has primarily been to support the Watershed Master Plan Program and other special projects. So I've been asked to give a brief overview of the Citywide Watershed Master Plan Program, how it originated, details about our wonderful team, and what we've been up to so far. Then Ed will describe the rain-on-mesh modeling that Freese and Nichols conducted for the program, and I'll close with next steps. The Watershed Master Plan Program in Fayetteville was initiated after several large events, including Hurricanes Matthew, Irma, Florence, and Dorian. This on top of recurring frequent flooding from smaller events. And that's something, we are all unfortunately very familiar with. This combination of these large storms and frequent flooding prompted us to go to council to ask for support to better understand and mitigate this citywide flooding. And we were very fortunate that our council had the vision to authorize a stormwater fee increase to help develop this effort. Of course, the primary goal is to identify potential projects that reduce flooding for inclusion in the capital improvement program and other programs. And as these projects are built, our public safety will be much improved and the city will be more resilient to future flooding events. So what does it take to take on something this large? I say it takes a village, and it's a huge team. So our team is guided by the city's Public Services Director, Sheila Thomas Ambat, and we're supported by the city staff, our program management firm, Freese and Nichols, several consulting firms conducting the watershed modeling, Arcadis, Gradient, HDR, Wilpert, Kimley Horn, Hazen and Sawyer, and 2 firms conducting detailed survey in the study areas, Stewart and ESP. So we understood, or rather quickly learned, that studying all 15 watersheds comprehensively would be a slow process, extremely expensive, and unnecessary in some cases. So in order to meet our objectives of using available resources and working within available funding, it was imperative that we develop an approach to prioritize the study areas. As one foundational element, citywide modeling was used to inform which areas should be studied in more detail. And Ed was going to talk more about one of those citywide modeling approaches in this presentation. And now we're 2 years into the program, and as we have developed the programmatic level foundational elements, we are moving and have moved into detailed watershed modeling. The first 5 watersheds under study include Blunt's Creek, Rockfish Creek, Cape Fear 2, Little Cross Creek, and Beaver Creek 3. Stormwater assets have been surveyed, stream assessments have been conducted, and H&H modeling has been completed. Ranking of concern areas is where we're at now, and concern areas the ranking is based on the severity of the problem, and I'll talk a little bit more about that towards the end. But in phase 2, then we'll be evaluating potential projects. So we're moving into phase 2 pretty quickly here, or have moved already with some watersheds. So with that, I'll turn it over to Ed to discuss their role in the program and the rain-on mesh modeling that helped identify and prioritize our study areas.
Thank you, Alicia, and good afternoon, all. A key step in any watershed master plan program is to identify and quantify flood risk. This discussion will focus on how Fayetteville performed that step. The city needed a way to objectively and systematically identify flood risk citywide to focus limited resources in high-risk flood areas. This was a large study area, greater than 150 square miles, and the cost to model the entire city in detail was just not feasible. Also, we could not just focus on the large storm event riverine issues. We need to understand the more frequent urban flood, standing water, summer thunderstorm issues. A comprehensive, efficient, planning level flood assessment tool was needed. The tool needed to handle storm drains and complex surface flow patterns, spatially varied rainfall, all on a 2D platform. Therefore, an ICM rain-on mesh approach was identified because it could efficiently assess a complex combination of storm drain systems, surface flow patterns, spatially varied rainfall, and spatially varied hydrologic losses over that 2D surface. And it could closely simulate observed events. It could incorporate the existing infrastructure, the pipes and nodes. And the spatially varied rainfall analysis available within ICM that is available is beneficial because it allows the model to be validated accurately for both historic and hypothetical storms. The data sources used for this analysis included the city's existing infrastructure files database, and we used mainly the main storm drain pipes 36 inches and larger, and culverts that were 24 inches and larger were included in the model. Now, this data was a little bit limited in that the vertical aspect of this information was not readily available. We used the terrain data set was the QL2 LiDAR from NC1 map. It was a 5x5 foot DEM. Rainfall depths were taken from Atlas 14 for the hypothetical events, the 10, 25, and 100 year. And for the actual events, for the hurricanes, the National Weather Service Stage 4 quantitative precipitation estimates were used. The land use files, the city had some existing land use files that we used within city limits, and this was supplemented outside of city limits where needed with NLCD data. Some of the model parameters and assumptions used. The model was built on a gridded mesh based on that LiDAR data set provided by the state. The gridded mesh itself, we can get into a little more detail, but I think the maximum triangle area, minimum element area, and maximum height variation parameters give ICM constraints for how to define the 2D unstructured mesh. That information is key, and the maximum triangle area used in this analysis was just over 2,100 square feet. The minimum element area was just under 1,100 square feet, and the maximum height variation within each element was set to 1 foot. And as previously mentioned, storm drain pipes 36 inches and greater, and culverts 24 inches and larger across the city were added. And then the soil and land use and impervious surface information was applied to the mesh to estimate runoff. The boundary conditions at the perimeter of the mesh were set to normal depth using an energy grade slope approximately equal to the ground slope. All channel and surface elements were modeled in 2D without 1D elements or bank lines. Now, obviously, there's some model limitations to this because it is a planning level assessment, and it's citywide, so it's large scale. So we were concerned with the large mesh size, or the large size of the model itself. Therefore, we had to go with a little larger mesh size, which does allow for the shorter computational times, but it does sacrifice some surface detail. But I think at this level, we were okay with that from a planning perspective. Also, due to the lack of the comprehensive vertical elevation data set, as I previously mentioned, the existing stormwater infrastructure, the inbred elevations for all the model assets were estimated based on a minimum cover assumption throughout the model area. Structures were imported into the ICM model as manholes, 2D node type with a flooding discharge coefficient of 0.5 and a 2D element area factor of 1. So that's what all the nodes are imported uniformly. When importing the storm drain system, the ICM head loss method at the upstream and downstream end of each pipe was set to normal with a coefficient of 1, which is the default value. These parameters provide a nominal amount of head loss appropriate for general application in the absence of site-specific information. So, and the model runs that were considered, we didn't want to run a bunch of storms through here because of the run times, and we just needed to focus in on what were the key events or the key design storms we needed to think about. And the 10-year and 25-year are basically the city's design storms for different features. So we obviously had to run those to see, what kind of level of service that was estimated in some of these areas. And we added the 100-year as a top-end type of storm. Historical rainfall from Matthew and Florence were run for validation purposes. Model output itself, ICM exports, or ICM produces depth polygons. These depth polygons were converted to depth grids for ease of viewing, I guess is more than one word. As you can see here, the depth polygons themselves are pretty jagged. Again, they're definitely more accurate, but in order to view these at a large scale, we wanted to be able to take a look at the polygons themselves, or the grids themselves, I'm sorry. So that increased resolution is necessary for the viewing. Citywide, so that's how the model is built, basically. The citywide rain-on mesh model looks, just from this scale, looked like a big mess. But as you zoom in, you can start to see some of the resolution we had here when you run this. Nothing earth-shattering here, but you can see the low-lying areas start to fill up as the rain falls onto the surface. So it's accurately estimating floods as they run through the system. So the model's built and run, and as efficient as we could make it. Again, the run times were about 8 hours. So these were not small models, but they had a lot of information in it, and we wanted to make sure it was validated information. So before significant decisions were made, the model needed to be validated. And the results were reviewed and vetted against historical flood issues. We had precipitation, those precipitation estimates from Matthew and Florence were run through the model and compared with flood reports from those storm events. Those flood reports included survey high watermarks from Hurricane Florence specifically. There were 12 high watermarks from that storm, and the model was within an average of 8 inches of those high watermarks. There was also anecdotal non-survey flood information available. These included flood emergency 911 calls, work order system data calls that included CityWorks and MainTrack, and then city staff, emergency responder, and NCDOT interview information. This anecdotal information totaled over 175 points citywide. The model Over 89% of the flood points of those 175 flood points were validated by the modeling. Another parallel program effort was a citywide hydrologic analysis. So this system, again, I think once we got the model validated, we felt pretty comfortable with it. We wanted a way to use that information to say, okay, we realize all this flood risk across the city. How can we organize it to say, these are the areas that we need to study most importantly? So there was another parallel program or effort, a citywide hydrologic analysis that had the city broken down into subbasins. And that gave us the granularity we needed to focus in on these areas. And these subbasins average about 80 acres in size at a citywide scale. So the results from the citywide ROM model were used to identify flooded buildings and road crossings in the 10, 25, and 100-year flood events. Those are noted by these features on the maps. The triangles, I believe, are road crossings, and the smaller dots are structures, buildings, and that kind of thing. So you can see the color-coded. The red means that it was overtopped or impacted by a 10-year storm. The orange means that it was impacted by a 25-year storm, and the yellow means it was impacted by a 100-year storm. These flood impacts in the subbasins were scored, totaled, and ranked to objectively prioritize each of these subbasins for more detailed study. The darker, the hotter the color, the purples and the pinks are the higher scoring subbasins, and the tans and grays are the lower scoring subbasins based on flood risk. So now that we've got we're comfortable with how the ROM model has produced prioritized subbasins across the city, and we've scored those and we're ready to move forward with some watersheds. We've discovered some other benefits the model could provide. Major event flood forecasting, emergency forecasting. The model can digest and run forecasted rainfall to identify the most at-risk locations in advance of the storm. This could help with staging emergency response resources and or road closures. Data for management and development purposes. This tool provides analytical flood information citywide, both upstream and downstream of potential new development. This can provide a good understanding of constraints prior to development, rather than discovering issues towards the end of the project. And city staff can also use the results of this citywide model where detailed studies are not planned or not available. And they can use it to help inform the day-to-day flood management issues throughout the city. It can also be useful when interfacing with citizens who bring drainage complaints. These can be verified without having to engage in a separate study that could deliver, unnecessarily precise results. So those are some additional uses and benefits of the model. Finally, before we turn it back over to Alicia, we wanted to mention that the citywide ROM model is a one-stop shop to identify, validate, prioritize flood-prone issues, flood-prone urban areas at a citywide scale. The analysis was comprehensive. It took in the whole city, and it resulted in about 21% of the city area was identified as a priority flood area and designated for more additional study. These areas will be studied in more detail to specify the flood issue and develop potential project solutions. The analysis was efficient. The total cost for this analysis was less than 6% of the overall program study budget. And the model identified significant areas that did not need additional study, saving the city an estimated 5 times the overall program study budget in future study costs. And we feel that the modeling was objective and defendable. Did not have to rely on the anecdotal flood reports alone. It provided tangible definition of flood risk citywide. And this, in turn, allowed the program to move forward confidently and informed to perform some more detailed analysis citywide. With that, I'll turn it over to Alicia to wrap us up. Thank you.
Thanks for all that information, Ed. So where are we now and where are we going? if you have a chance or had a chance to listen to Arcata's presentation on their work in the Blunt's Creek watershed, that'll help understand some of the other aspects of the modeling effort that's ongoing. So this flow chart we're including here to show that as a team in phase 1, we're moving forward with identifying concern areas in several watersheds. And then from there, we're using the severity or ranking of severity of the concern areas, truly what the problem is and how bad is it and what type is it, to decide whether or not to move forward with potential projects. And when I say severity of the problem, we're using lengths of lane impacted, hazardous crossings, the depth and velocity, number and type of structures impacted, including essential facilities and access concerns. And we're also looking at impacts to streams. So how do we do it, or what are we doing? Just in a nutshell, the city is reviewing the concern areas with the team. And then with our combination of institutional knowledge and the modeling results, we help determine whether or not to move forward with evaluating potential projects. And then once that decision is made, the consulting team moves into refining and modeling selected potential projects, including considerations for future conditions, economic development overlays, and developing opinions of probable cost. Projects will then be prioritized and included in the CIP or other programs. With that, I'd like to thank our entire team for all the hard work that they've been putting into this program. It's been moving pretty fast, as Ed could tell you. I want to thank Ed again for his presentation, and thank you for your time. We'll take any questions you may have now.
Thank you, Ed and Alicia, for your time today and for your helpful presentations on the decisive action taken by the city of Fayetteville in planning and mitigating for future flooding events. We received several questions for you. The first one asks how the flows in the creek, which were outside city limits, applied in the model.
Sure, thank you. The majority of the modeling was contained within, was in the model. So just outside the watersheds themselves drained into the city, and we were able to capture the entire watershed. The only one that was too large to take was the Cape Fear River, which runs to the east, and that we used an inflow hydrograph for that.
Okay, and did you use smaller mesh size in some specific areas?
No, this was a planning level analysis, and it was meant to be equally applied across the city. So we kept that same application across the city. There was no specialized areas.
Okay. And similar to Rupali's question, were there any upstream offsite watershed contributing to your citywide rain on grid model?
Just the Cape Fear, as mentioned previously.
And was the maximum size of model areas and numbers of stormwater elements?
We did run up against the limit in our ICM license, so we did, and the city happened to split into very convenient separate watersheds. So the model was split into two separate ICM models to make sure that we could fit within the constraints.
Okay, and Clark asks, how does the ICM model handle the interface between the 2D rainfall, overland flow, and the subsurface storm sewer system?
Yeah, I knew we were going to get into something this detailed, and I don't have my modeler here, so I don't have an answer to that question right now, but I can certainly follow up with it.
Okay. And that's all the questions that we have in the queue. So if you have a question that you can pose very quickly, we'll see if we can get our presenters to answer. Okay, nothing new is coming in. I want to thank our speakers for their great presentations. Be sure to join your presentation choice during section J, the last session of the day. Thank you. Karen McHugh signing off.